Look at Jupiter through a small telescope, and one feature can make the whole planet feel alive. A red storm so large that Earth could fit inside it. For generations, it has looked almost permanent. It appears in old drawings, modern telescope images, spacecraft photographs, textbooks, posters, and documentaries about the solar system. It feels less like weather and more like a landmark. But that feeling may be wrong. You may be living during the closing era of the Great Red Spot. Not a storm that lasted a weekend, not a hurricane that survived one season. A storm that may have raged for centuries could fade within decades. Some estimates suggest it might disappear in as little as 20 years. That means one of the most famous sites in the solar system could vanish while people alive today are still looking up at Jupiter. And the loss would be more than visual. The Great Red Spot is not just a beautiful oval on a giant planet. It is a natural laboratory. It is a clue to how huge rotating atmospheres behave. It is a test of how storms survive without land, oceans, or seasons like ours. And it is a reminder that the universe does not keep all of its evidence available forever. To understand why this storm exists at all, start with Jupiter itself. Jupiter is enormous in a way that is difficult to picture. It has about 2.5 times the mass of all the other planets in the solar system combined. Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune together still do not outweigh it. By volume, Jupiter could hold roughly 1,300 Earths. It is made mostly of hydrogen and helium, the same simple ingredients that dominate stars. But Jupiter never became a star. Instead, it became a giant world where pressure, rotation, and chemistry turn weather into something like planetary machinery. Far below the visible clouds, hydrogen is squeezed into extreme states. Under enough pressure, it becomes liquid. Deeper still, it becomes metallic hydrogen, meaning it can conduct electricity even though it is still hydrogen. Above that strange interior, the atmosphere is constantly stretched and twisted by Jupiter's speed. A day on Jupiter lasts only about 10 Earth hours. That is less than half of one Earth day, even though the planet is more than 11 times wider than Earth. At the equator, its clouds race around the planet at roughly 43,000 kilometers per hour.
Jupiter is the fastest spinning planet in the solar system. That rapid rotation helps carve the atmosphere into bands, jets, belts, zones, and spinning vortices. Jupiter does not look like a smooth marble because it is not behaving like one. It looks like a living engine. And inside that engine sits the Great Red Spot. The Great Red Spot is a high-pressure anticyclone. On Jupiter, it rotates counterclockwise and completes one turn in about 6 Earth days. But that does not mean it is gentle. Winds around its outer edges can exceed 640 kilometers per hour. On Earth, winds like that would be beyond catastrophic. On Jupiter, they are part of a storm that has outlasted human empires. So why has it survived so long? Earth's hurricanes feed on warm ocean water, weaken over cold water, slam into land, and eventually fall apart. Jupiter has no solid surface for the Great Red Spot to hit. There are no continents to disrupt it. No mountain ranges stand in its way. The storm floats inside a deep, layered atmosphere, held between powerful jet streams moving in different directions. Imagine a spinning object trapped between two massive conveyor belts. One belt pushes one way, the other pushes the opposite way.
Between them, the vortex is squeezed, spun, and kept in place. Jupiter's fast rotation strengthens the Coriolis effect, the same broad force that helps organize storms on Earth, but on Jupiter, it acts across a far larger stage. That combination lets a vortex live far longer than any storm we know on our planet. But long-lived does not mean immortal. And the evidence that the Great Red Spot is changing is written directly into its size. Modern measurements show the storm is about 16,350 kilometers wide. That is still wider than Earth. It also reaches more than 350 kilometers down into Jupiter's atmosphere. For comparison, most of Earth's familiar weather happens in the troposphere, a layer only about 8 to 15 kilometers thick, depending on where you are. Jupiter's famous storm extends downward through a depth that makes Earth's weather layer feel like a thin skin. But the storm used to be much larger. In the 19th century, astronomers estimated that it was about 48,000 kilometers wide. That is more than 3 times Earth's width. So the gigantic storm we see today may actually be the shrunken version. For decades, it has been losing width. Its shape has changed too. It was once a stretched oval. Now it is becoming rounder. That may sound harmless, even tidy, but to scientists, shape is not cosmetic. A vortex's shape is tied to its energy, its internal structure, and the winds that keep it organized. If a giant storm becomes smaller and rounder, it may be entering a different and possibly less stable state. From far away, it still looks powerful. Inside the physics, it may be weakening. Its color has changed as well. The Great Red Spot is famous for being red, but it has shifted between deep red, orange, salmon, and pale beige. Sometimes it stands out sharply from the surrounding cloud bands. Sometimes it fades until it almost blends in. Scientists are still studying exactly what creates those colors. The answer likely involves chemistry, sunlight, altitude, and compounds altered high in Jupiter's atmosphere. But the larger point is simple. The Great Red Spot is not a frozen painting. It changes, it evolves. It may be aging before our eyes. And that leads to a deeper historical mystery. Is the storm we see today truly the same one astronomers observed in the 17th century? In 1665, Giovanni Cassini observed a spot on Jupiter. He and other early telescope users helped reveal that Jupiter was not just a bright point in the sky, but a world with visible features. That old spot is sometimes linked to the Great Red Spot. If the connection is real, the storm could be about 350 years old. But there is a problem. After those early records, there is a long gap. A similar feature is not clearly recorded again until 1831. That leaves more than a century and a half of uncertainty. Some researchers think Cassini's spot and the modern Great Red Spot may not be the same storm. The earlier spot may have faded or collapsed. A later storm may have formed in a similar region and inherited the legend. If that is true, Jupiter may already have lost one giant storm before we understood how it ended. That possibility matters because it means the current Great Red Spot is not guaranteed to survive. We have seen giant storms disappear elsewhere. In 1989, Voyager 2 flew past Neptune and photographed a huge dark feature in its atmosphere called the Great Dark Spot. It was dramatic, planet-sized, and instantly iconic. Then astronomers looked again. By 1994, it was gone. Not slightly changed, gone. A storm large enough to define Neptune's face in a spacecraft image had vanished in only a few years. That is the difficult truth about studying nature.
It does not wait for better instruments. It does not pause until the next mission is ready. It does not preserve every experiment for our convenience. Sometimes a phenomenon appears, teaches what it can, and disappears before we have finished asking questions. That is why the Great Red Spot matters scientifically. It is not only a postcard feature. It lets researchers study conditions that cannot be recreated on Earth. Infrared observations reveal different layers of Jupiter's clouds. They show how heat moves, how cloud decks stack, and how material circulates in a gas giant atmosphere. Because the Great Red Spot is so large and long-lasting, it gives scientists a rare, steady target. A small storm gives a snapshot. The Great Red Spot gives a long story. NASA's Juno spacecraft added a new level of detail. Its close passes helped show that the storm is not merely a surface pattern. It has deep roots extending hundreds of kilometers down. Above it, scientists found another surprise. The upper atmosphere over the Great Red Spot is unusually hot compared with much of Jupiter. One explanation is that turbulence in the storm creates waves that carry energy upward, heating the gas above. A storm wider than Earth may be warming the sky over itself with energy produced by its own violent motion. That is not something we can study by waiting for a thunderstorm outside. Jupiter turns fluid dynamics into a cosmic scale experiment. And fluid dynamics matters far beyond Jupiter. The same broad physics helps describe atmospheres, oceans, storms, jet streams, and rotating systems throughout the universe. Jupiter is not Earth. It has no oceans like ours, no continents, no breathable air, and no solid ground beneath those visible clouds. But the mathematics of rotating fluids connects the two planets. When scientists study how a vortex survives on Jupiter, they sharpen tools used to think about rotating flows here at home. One Earth connection is atmospheric blocking. A blocking pattern happens when a large, high-pressure system stalls and forces weather to linger. Instead of moving along normally, heat, cold, or rain can remain trapped over a region. That can turn ordinary weather into a dangerous event. So what can a red storm on Jupiter teach us about a heat wave on Earth?
Jupiter does not control our weather. The connection is not mystical, it is physical. Both systems involve rotation, pressure, jet streams, persistence, and the movement of energy through fluids. By studying an extreme case like the Great Red Spot, researchers test ideas about how large circulation patterns survive and how they break down. Better models can have real consequences. They can improve thinking about heat waves, stalled weather systems, rainfall extremes, and risks to food production. In some severe blocking events, crop losses can reach millions of tons. So the Great Red Spot is far away, but the physics it reveals belongs to the same universe we live in. And right now, that laboratory is shrinking. Imagine a scientist decades from now reading the record of its final years. Width decreasing, shape tightening, color shifting, winds evolving. Then one day, no Great Red Spot, only smaller storms, only archived images, only measurements collected while it was still there. That is where the story becomes larger than Jupiter. The Great Red Spot is a local example of a cosmic rule. Observations can expire. We often think of space as timeless. Stars look ancient, planets seem permanent. Galaxies appear frozen in deep photographs. But the universe is not a museum. It is changing, and some things visible today will not remain visible forever. The biggest example is cosmic expansion. Space itself is expanding, and that expansion is accelerating. Over immense timescales, many distant galaxies will be carried away so fast that future observers will no longer be able to see them.
Today, telescopes can map a vast cosmic web. We can study galaxies, clusters, filaments, and voids across enormous distances. Those views are not just beautiful, they are evidence. They show that the universe has a history. They help reveal that it was once hotter, denser, and more compact. But imagine a civilization 2 trillion years from now. By then, most distant galaxies may have slipped beyond view. The local group may have merged into one huge system. The broader cosmic web could be hidden behind the horizon of an expanding universe. To those future observers, the sky may look far emptier, not because the universe was always simple, because the evidence moved out of reach. They might have brilliant instruments and still miss the fact that billions of galaxies once filled the observable sky. Their science could be limited not by intelligence, but by timing. Knowledge depends on when you arrive. You need curiosity, but you also need the clues to still be visible. The cosmic microwave background is another example. This faint radiation is one of the strongest pieces of evidence for the Big Bang. It is the cooled afterglow of the early universe. Today, we can detect it across the sky. Cosmic expansion has stretched it into microwave wavelengths, but it is still measurable. It helps scientists estimate the age, composition, and early conditions of the universe. But expansion continues. That ancient light keeps stretching. Its wavelengths grow longer. Its signal becomes weaker. In the far future, it may become effectively undetectable. One of the clearest fingerprints of the Big Bang could fade beyond the reach of any instrument. That does not mean the Big Bang did not happen. It means future observers may not have the same evidence we do. They may inherit a universe with missing records. And suddenly, the Great Red Spot feels less like a distant curiosity and more like a warning label. Not a frightening one, a humbling one. Even enormous things can be temporary. Even famous things can vanish. Even evidence can have a deadline. Think about what humans can do right now. We can point telescopes at Jupiter and watch a storm that may have roots in the earliest age of telescopic astronomy. We can compare modern data with old drawings and measurements. We can send spacecraft like Juno close enough to measure structure, depth, heat, and motion. We can track the storm's shrinking width across decades. We can watch how it interacts with surrounding jet streams. We can study its color, its winds, and its possible decline. That is an extraordinary privilege, and it sits inside an even larger privilege. We live late enough for telescopes, spacecraft, spectroscopy, mathematics, and computers to exist. But we also live early enough for the universe to still display many of its ancient clues. Stars are still forming in nebulae. Galaxies are still visible across deep time. The cosmic microwave background is still detectable. Jupiter's most famous storm is still there. For now. This is a rare window when humans can study a shrinking storm next door and the afterglow of the beginning of everything. That window will not close all at once. The Great Red Spot may fade over decades. Distant galaxies will disappear from practical observation over unimaginable spans of time. The cosmic microwave background will weaken over timescales far beyond human history. But the pattern is the same. The universe offers evidence, but not permanently. That makes observation a responsibility. Every measurement matters more when the object might not last. Every image becomes more than a picture. It becomes a record future scientists may need. If the Great Red Spot disappears in 20 years, or 50, or 100, the best version of it will survive only in the data collected while it was active. Its changing size, its wind speeds, its depth, its temperature patterns, its color shifts, its relationship with Jupiter's bands, its possible final collapse. If Cassini's old spot truly was a different storm, then history already gave us a warning. A giant feature may have come and gone while records were too limited to capture its ending. This time, we have better tools. We have spacecraft. We have global observatories. We have centuries of comparison. We have the chance to watch carefully. The question is not whether the Great Red Spot deserves attention because it is beautiful. The question is what we lose if it disappears before we understand it. The answer reaches from Jupiter's cloud tops to Earth's climate models, from planetary science to the nature of evidence itself. Science can feel like collecting facts from a permanent warehouse, but the universe is more like a library where some pages fade, some shelves drift away, and some books were never copied in time. That sounds dramatic, but it is also motivating. It means our era is not ordinary. It is an observational sweet spot. The solar system is close enough to explore. The cosmos is still rich enough to decode. Our tools are finally powerful enough to notice what is changing. The Great Red Spot may have spun while the first telescopes were aimed at Jupiter. It may have endured through sailing ships, electric cities, rockets, and spacecraft. Or it may be younger than its legend, a later storm that rose after an earlier one vanished. Either way, it has become one of the most recognizable planetary features ever seen. And now it is smaller than it used to be. Its oval has tightened, its colors have shifted, its future is uncertain. But that uncertainty is exactly why it is worth watching. If it survives, we learn how giant storms endure. If it fades, we learn how giant storms die. If it transforms, we learn that even the solar system's icons are more dynamic than they appear. The next time you see an image of Jupiter, do not treat the Great Red Spot as decoration. Treat it like a countdown. Not a countdown to disaster, a countdown to discovery. A countdown to record what can still be recorded. A countdown to understand a storm no human could stand inside, but whose physics can still teach us about worlds, weather, and time. Right now, a storm wider than Earth is spinning on a planet that could hold 1,300 Earths, in winds faster than 640 kilometers per hour, and it may not be there much longer. That is the strange gift of this moment. We are not only alive while Jupiter has a Great Red Spot. We are alive while it is changing fast enough for one generation to notice. And on the largest scale, we are not only alive in the universe, we are alive while the universe is still willing to show us some of its oldest evidence. Future observers may make brilliant discoveries. They may explore worlds we will never reach. They may build instruments we cannot imagine. But some things available to us may be gone for them. Some storms will fade. Some galaxies will slip away. Some ancient signals will stretch into silence. So when we look at the Great Red Spot, we are seeing more than weather. We are seeing a reminder that even the grandest landmarks are temporary, and that looking now can become a gift to everyone who looks later.